Good afternoon, everyone. A warm welcome from InfoChips. Thank you for giving this webinar. Thank you for joining this webinar on overview of telecom technology 5G infrastructure, part 1, presented by InfoChip and IESA Gujarat Chapter. Today we have Dr. Yash Vasavada with us. He has done MS and PhD in electrical engineering from Virginia Polytechnic Institute and State University, USA. He is currently an associate professor at DAIICT. He works in the areas of communication system design and application of machine learning algorithms to communications and signal processing. He has over 20 years of experience at Hughes Network System in Germantown, Maryland, USA. There he has worked on design, development and deployment of a number of GEO, MEO and LEO satellite systems. At Hughes, he was the recipient of 8 Hughes Patent Awards. Now, I would kindly request Dr. Yash Vasavada to continue our event by sharing his valuable knowledge with us.
Hello, welcome everyone. Uh, I'll, Over the course of 2 days, today and tomorrow, I will be presenting an overview of telecom technology as well as 4G, 5G, what is known as 5GB, 5G and beyond, as well as 6G. Okay. Uh, so this is the outline of my presentation. I'll briefly introduce myself. I'll have a vision statement. And then maybe take a conceptual look at several of the enabling technologies for the 4G, 5G, and 6G communications, such as LDPC cores, the OFDM technology, the BIMO systems, etc. And then maybe at the end, there'll be a brief section on the 5G network design. Okay. So the way I have planned it is that the first few sections that are outlined here, I'll be covering today. And then tomorrow I'll be covering the topics of OFDM, MIMO, and 5G networks. Okay. So as Anjali introduced me, I have worked previously at a company called Hughes Network Systems, where I was affiliated. I was affiliated with Hughes from 1996 onwards until 2016. And I worked over a number of mobile satellite communication systems, GEO systems, MEO, and low Earth orbit LEO systems. And my role there was as a systems engineer, and I developed physical layer and MAC layer, network layer algorithms. And then since 2016, I'm with DICT, and I mainly work in the areas of communication, signal processing, and machine learning. And I am also affiliated with Virginia Tech, which is the university from where I pursued my master's and PhD degrees. And my research area is generally in the domains of statistical signal processing, adaptive beamforming algorithms, message passing algorithms, so on and so forth. These are some of my recent publications over the last 2 years. Just to give you a quick overview, I worked in the domains of spatial modulation MIMO, 5G LDPC code, some smart decoding algorithms for them based on the smart algorithms, machine learning, as well as some sub-Nyquist spectrum sensing of sparse wideband signals. And recently, I've published multiple conference papers on compensation for amplifier nonlinearity, hybrid beamforming from MIMO, and so on and so forth. Okay. In terms of the communication infrastructure, this is a very pervasive diagram. It is sort of a subset of the 7-layer OSI model that many of us are familiar with. And my areas of focus is mainly on the MAC and the physical layer. Okay, so this is just to give you a brief background of where I'm coming from, both academically as well as professionally. So now I will start my main presentation. The first part of the presentation today will be kind of a non-technical in nature. And I want to describe what the vision is in terms of the futuristic human society, and basically how some of this vision statement, some of the goals are going to be accomplished by a very powerful communication technology, some of which we already are starting to enjoy today. Okay, so that is the content of this first part of the presentation. See, in terms of data connectivity, in terms of wireless connectivity, we think that we are already kind of doing pretty well in terms of how much data rate we can get on our phones and on our Wi-Fi systems, our landline connections. But at least in terms of wireless terrestrial infrastructure, the best is maybe yet to come, right? We are here at about 12.1 gigabit per month in terms of per subscriber traffic volume. And the projection is almost an exponential growth over next maybe 8 to 10 years, right? So as a popular Hindi song says, party to abhi shuru hui hai, right? The game is still is just beginning, and there is a real terrific increase projected in terms of wireless connectivity in maybe next 5, 10, 15 years or so. In terms of mobile subscription, in terms of smartphone subscription, in terms of machine type connectivities, the traffic volume, the traffic per subscriber. This chart shows where we were in 2010, where we are in around 2020, 2022, and where the projection is in terms of next 10 years or so, right? So there is almost a doubling of each of these numbers, or maybe sometimes quadrupling of these numbers, especially in terms of machine-to-machine communications, the IoT, the Internet of Things, and the sensor networks. The projection is really, really exponentially growing in nature, right? From maybe a fraction of billion to maybe 7 billion to close to 100 billion devices will be IoT type of devices. So the way the vision is in terms of how the communication services are going to be enabled, this is again a kind of well-known, nowadays it's a famous triangle for at least those of us who are in communication and signal processing domains. ITU, International Telecommunication Union, has come up with this vision statement, sort of a triangular concept in nature. There are 3 main areas: enhanced mobile broadband, massive machine type communication, and ultra reliable low latency communication. And the variety of services that our society will then start enjoying and making use of fall somewhere within this triangle as a different weightage of these different vertices. So self-driving cars would be more empowered or enabled by URLLC type of communication links, whereas smart city concepts will be driven by MMTC. And 3D video, ultra high definition screens, etc. will be driven by more of enhanced mobile broadband. The 3 key terms are, again, ubiquitous mobile ultra broadband. The goal is that the mobile devices, not the tethered devices, not the wireline devices, but without wireline connectivity, we want to provide ultra broadband connections, very high data rate, and it should be ubiquitous in nature. So you could be traveling in a train, you could be in between some big towns in pretty much remote rural areas, and you should still get very high data rates. Ultra high speed with low latency communication. So that is the other paradigm, and that is what would enable, for example, a self-driving car or an industrial automation type of application. So UHS LLC or combination of it with URLLC is the other main feature. And then the third is this massively built sensor networks, MMTC, ultra high density communications. So that will enable the growth of the smart cities, smart homes, smart building type of applications. Okay, so the EMUB feature, enhanced mobile ultra broadband feature, the goal is to provide maybe as much as 1 gigabits per second data rate anywhere. And then maybe overall network level connectivity would be on the order of a terabits per second. And there, the technology vision is that the current networks, for example, terrestrial networks, satellite networks, airborne, what are known as HAPS, high altitude platform-based networks, which include the drones, unmanned aerial vehicles. This all will be integrated into a unified whole, right? So users will move seamlessly between terrestrial network when they are in some cities and towns. And then when they go to some remote area, rural areas, maybe satellite-based network or airborne network, will provide them the same type of data rate as they would be enjoying when they are in cities, but without their awareness. They wouldn't even know that they have been moved from terrestrial to satellite to airborne, etc. From Internet of Things now, the vision is to not only consider them as a connected network of things, but connected network of intelligence, right? So there, the sensor data will not be just considered in an atomic manner, but it will be continuously analyzed, and some conceptual insights will be collected throughout the network, right? So that is the vision in terms of not only doing the sensor data collection and communication, but also derive some larger intelligence from it. Ultra long battery life, and for that there is a concept called wireless information and energy transfer. So not only the data, not only the information, but also the energy will be transferred wirelessly, and so that will empower battery lives that are much better than what we have today. Energy harvesting schemes are a whole new research domain. There are many research initiatives that have been taken worldwide. Highly accurate localization. So there the goal is that the positioning technologies that we have today, including the radar, they will all be integrated with the mobile networks. And so basically the goal is that we want to provide potentially a large network with a large number, a massive number of connected devices. Some of them may be just machines, there may be some sensors or things that are then connected to the overall network with end-to-end delay or latency, which are much better than what we have now, maybe an order of magnitude better. And these connections, the connectivity is highly reliable. And there are a lot of technologies that are currently being developed and will continue to be developed for next 10, 15 years, which will be sort of in the background, kind of behind the curtain, so to speak, for the end users. Small cell access points and networks, high capacity backhaul using either optical fiber or FSO type of techniques, and then network softwareization and virtualization, right? So these are some of the research domains that are highly active. Again, some of the applications in terms of 5G and beyond and 6G. One area there which We all have heard about Facebook has renamed itself as Metaverse or Meta Technology Company. There, the gambit of the technologies fall into these three different areas, which are kind of overlapping with each other. Extended reality is considered to be a futuristic technology, a mix of augmented reality, where your actual view of the real physical world will be augmented by some computer-generated inputs and audiovisual graphics. And one example that you may be familiar with is that today, if you walk into a furniture store, you can maybe superimpose the layout of furniture on an image of your drawing room, right? So that is an example of AR, but that is just thought to be a beginning type of technology. There are many other applications that are being envisioned in terms of AR. Virtual reality is again where people wear some VR headsets and they generate through the VR headsets, they are able to experience some real world type of experiences through a completely virtual environment, right? And their one goal is that a VR environment will engage all of our 5 human senses. And so it will be kind of an immersive environment, which will be entirely virtual in nature. And then mixed reality is a combination of the real and the virtual worlds that interact with each other. And the supporting technologies are VR headsets, wearable technologies, haptic communication, touch-based real-time communication, brain-computer interfaces. So these are some of the technologies that we will start seeing develop and become more mature over a period of next several years. And there, the enabling technology that will be kind of behind the curtains, so to speak, will be this UHSLLC, URLLC type of communication technology that will be part of 5G and beyond type of networks. Continuing on in terms of the futuristic vision, connected robotics and autonomous systems. They include, for example, self-driving cars, smart factories, which are envisioned as part of Industry 4.0 framework, and UAV-assisted communication to enable military surveillance, smart agriculture, law and order type of surveillance, product delivery, disaster management. Healthcare and biomedical application is a different vertical where the goal would be to perform surgery remotely, maybe health monitoring, medicine delivery, and medicine application, etc., all in a remote manner, right? So the doctors and the nurses may not have to be physically co-located with where a patient is. And this whole new concept of that is still currently being developed, the concept of smart cities and societies, where there will be a massive number of embedded sensors, sort of the Internet of Things, to provide not only measurements and monitoring, but there is some newer version of this technology, which is called cyber physical systems, which will also be able to control the devices in a feedback control loop manner. Okay, so there the ultra wideband mobile communication and the MMTC communication aspects of that triangle, the ITU triangle that we looked at few slides back, are going to bring about this type of technological revolutions. This is one chart that shows that some of these technological goals, societal goals, are already kind of beginning to get realized with 5G. But in terms of, for example, AR or telepresence, surveillance type of applications, automation, energy efficient devices, the connected robots, etc., biosensors, where 5G is going to be far more improved by the time 6G gets realized. Okay, so that the ambition is very very high, and the goal is to bring about these technological revolutions that will potentially transform our human society, and that might happen maybe in just near future. And this is just a vision graphic that shows how all of these different technologies that will empower the next revolutions in the way we live and the way we function, how all of them are going to be ultimately driven by underlying high capacity, high throughput, highly reliable, low latency wireless communications. Okay, so so that concludes the first part of my talk. Now for next maybe about half an hour or so, let me take maybe more of a conceptual look at some of the enabling technologies for 4G, 5G, and even for the next generation 6G and beyond type of systems. Okay, so in order to realize some of the technological advances that we just now saw, the wireless technology has to improve in multiple different aspects, and those are summarized on this chart. For example, in terms of peak data rates, maybe we are currently somewhere around 1 gigabits per second, but we want to improve it by an order of magnitude or even more. User experience data rate, spectral efficiency in terms of supporting user mobility, in terms of reducing the delays that are experienced over communication network, in terms of energy efficiency, in terms of connection density. Everywhere the goal is to go from the orange color bars where we were maybe just a few years back to maybe blue colored bars, which are either currently being realized or will be realized as part of 5G and beyond type of connectivities. This is sort of a different visualization of the previous chart. All these different metrics are represented by this hexagonal pattern in terms of where the technology was for 5G, for 3G and 4G, and where the projection are in terms of 5G and beyond. Okay, now what you will notice is that in many of these performance metrics, the peak data rate of 20 gigabits per second, the user experience data rate of maybe 1 gigabits per second with 100 users simultaneously operating, spectral efficiency, right? These are some of the key metrics that need improvement and for which the technological advances have to be there. And so I wanted to now spend some time in looking at the fundamental concept, okay, in terms of how can we achieve this type of data rates? How can we increase spectral efficiency? How can we increase area traffic capacity? And if you recall, all of these goals have to be achieved with very, very high reliability in terms of message transfer, in terms of data transfer. If suppose somebody is able to transmit 1000 megabits per second, but the reliability is poor. And so out of 1000 megabits that are being transmitted by the sender every second, if half of them are corrupted, half of the bits get corrupted, then such a communication technology is not very useful, right? As we all know, if we are trying to even today watch some videos or do some large size file transfer on the internet, and if connectivity is poor, there are a lot of errors, then the images and the videos don't turn out right. They either buffer or there are some low resolution images that we see. The goal is that we want to be able to achieve this type of data rates this type of capacity or efficiencies while maintaining extremely high reliability, right? I think in one of my earlier slides, the goal mentioned there was some 99.999%, 99.99999% reliability. Okay, extremely reliable links is the goal. So in that regard, I would like to now switch over to a little bit of a technical type of presentation. Okay, let us see. This. Okay, so I'm going to take a little bit of a conceptual look at one key enabling technology, which is known as forward error correction coding. This is considered to be a major driver of going from 3G to 4G to 5G to 6G, how the technology is going to improve. Okay, so let us take a look at it. This entire technology called forward error correction coding, FEC coding, or channel coding, the purpose is to turn a noisy channel, which introduces errors in the transmitted symbols, to ideally a noiseless channel, right? That is the goal. And the motivation is extremely clear. If that ideal goal is realized, then you would not hear any disturbances when you are talking on the phone, although the actual channel might be impairing your signal and distorting your signal and corrupting your signal in many different manners. Right? There is fading going on in the wireless links. There are non-linear distortion happening. There is just some thermal noise that gets introduced. Maybe the power that you get is not enough. In presence of all of this type of impairments, if the goal of this technology, the FEC technology, if it is realized, then you as an end user, you would not see any of that. What you will see is perfect voice conversation or video downloads. And more importantly, for 5G, 5G and beyond, as we said, one target is ultra reliable communication where, for example, if you take the application of remote surgery, there the link better be very, very, very error proof, right? So it's, although the actual communication link will be introducing the noise, the bits that ultimately get transferred should be received nearly perfectly. And so the goal of the channel coding is to turn the real world channels, which are always imperfect, which are always noisy, they have all sorts of impairments, to an ideal channel which appears as if it does not suffer from all of these imperfections, right? And a lot of the times we will talk about the noisiness of a channel in terms of the signal to noise power ratio, SNR, which is measured at the receiver. Okay, so this we will get into it little later today, hopefully, if I have time to do that. And the goal of channel coding is to turn an actual physical communication channel, which may be experiencing a bad SNR which is pretty low, into an encoded channel, a protected channel, if you will, whose performance is actually as if the channel has a very good SNR. Okay, so that is the main idea of this channel coding scheme, and the whole smartness and the intelligence and the clever mathematics that people have developed over a number of years is trying to solve this essential problem. How to make a channel with bad SNR turn into a channel with as if it is a good SNR channel, sort of a virtual channel, which appears as a very good channel to the end user. Now, as you all might have observed earlier, right? Whenever a topic which is sufficiently complex is presented to you and you are kind of learning it for the first time, maybe the best way to begin is to start with something very simple. If you understand the simple concept which lies at the heart of any complicated subject, then maybe 80% of your task is done. You can then add complexities, maybe sort of a layer by layer manner. And so likewise here, to understand what is needed of such a FEC technology, let us consider a very simple model of a noisy channel. It is called binary symmetric channel. And all that it does is it flips randomly the bits that are transmitted. So some zeros get turned into 1, some ones get turned into 0, and the receiver doesn't know which bits are getting flipped by the channel. The question is, when this is happening, when the channel is this binary symmetric channel which flips the bits, is it possible for the receiver to undo this effect, right? And so at first it appears that task is pretty much impossible, if not very difficult, because the channel has already flipped the bits and the receiver doesn't know which bits are flipped. So how can the receiver magically undo the effect? Well, then if you look at the problem a little closely, you will see that the reason why the receiver makes the error where when it gets certain bits at the receiver, it cannot decide when suppose at the receiver I get a bit y equal to 0, because the channel is this BSC type of channel, it is flipping the bits randomly. When I get y equal to 0, I don't know whether the transmitted bit was x equal to 0 or it was actually x equal to 1, which got flipped into a bit 0 at the receiver, right? So that is the underlying error phenomenon that is happening. And so once we look at the concept behind the errors that such a bit flipping channel introduces, we can then say that maybe if we can somehow turn the channel of this previous diagram into one that looks like this, right? So the sender still sends a bit at a time, maybe 0 and 1. But the receiver somehow, if it gets 4 possible outputs, not just 2. And let's say those 4 outputs are 0, 0, 0, 1, 1, 0, and 1, 1. And suppose if we can somehow make sure that when bit 0 is sent, the receiver either gets 0, 0 and 0, 1. And when the bit 1 is sent, the receiver gets 1, 0 and 1, 1. Then if suppose something like this can be realized, then you will, it will be easy for you to accept that now my channel has become noiseless. Although the actual physical channel is introducing noise by means of these red colored arrows, the receiver is with 100% certainty it is able to say which bit was transmitted. If it receives 0, 0 or 0, 1, then it will say that bit 0 was transmitted. If it receives 1, 0 and 1, 1, then it knows that bit 1 was transmitted. Basically, there is no loss of confidence. There is no uncertainty at the receiver in terms of which bit was transmitted after it receives this pattern of 2 bits. Basically, we are taking all the possible binary sequences that the receiver can see, 2-bit sequences, and we are dividing into 2 non-overlapping subset. And this non-overlapping nature is what allows us to say that there is not going to be any error pursued by the receiver, although the channel is introducing noise. Now, obvious question is that how can this be done then, right? We actually just want to transmit bit 0 and 1. How can we make sure that the receiver sees this 2-bit pattern, and how to make sure that, for example, bit 0 doesn't turn into 1 0 or 1 1? How to ensure this non-overlapping subsets? Okay, so the idea here is what is known as a repeat coding or repetition coding. And what we had on the previous slide is called repeat by 2 coding. We take one bit and repeat it 2 times. If we extend this coding, for example, instead of repeat by 2, if we consider repeat by 3 coding, right? Then maybe you will start getting the idea of what is actually practically possible. What we do is when we want to transmit bit 0, we repeat it 3 times. So 0 gets transmitted as 0 0 0. When we want to transmit 1, we repeat it again 3 times, and so 1 gets transmitted as 1 1 1. And so the receiver now gets 3 bits at a time. Receiver is looking out for 3 bits, 3 consecutive bits. Now, the channel is still flipping the bits randomly, but the receiver has now some degree of protection, right? So if bit 0 gets received as 0 0 0, then the receiver has no confusion. But even if 1 bit gets flipped, right? So 0 0 0 turns into 0 0 1, 0 1 0, 0 1 1. Then also the receiver can say with a high confidence that it's most likely bit 0 that was transmitted, right? And similarly, when 1 bit gets flipped, when the receiver transmitter sends 1, then the receiver can say with high probability that bit 1 was transmitted. So the green and the red colored arrows are the reception scenarios in which there are not going to be any errors. The black colored arrows are where the receiver will still be confused and it can still make errors, right? So with repeat by 3 coding, you can overcome some bit flippings that are happening, but not all. The receiver will need a slightly smarter algorithm than if you suppose didn't do this repetition at all. But this is a pretty simple algorithm. It's just basically majority voting, right? If you get a 3-bit sequence, you look at whether 0 is happening more time or 1 is happening more time. And so if number of zeros is greater than number of 1, then you say that bit 0 was transmitted. If number of 1 is greater than number of zeros, then you say bit 1 was transmitted. So this is the majority voting decoding scheme. Now, a little bit of math, I'm not going to describe it. Those of you who are mathematically inclined, you can do this math on your own. What we are going to now say is that what is the price that we pay, right? So if we didn't do this repeat, we could have transmitted 3 independent bits of information. Basically, our efficiency would have been higher. By repeating, we are making use of the channel 3 times, but we are not transmitting anything new. We are just sending the same bit again and again. So that loss of efficiency is measured by what is known as the rate of the channel coding, K divided by N. And for the repetition coding, K is 1. I'm transmitting only 1 bit at a time. And capital N is 3 because I am repeating 1 bit 3 times. And so the rate becomes 1 over 3. In general, rate measures the efficiency of the coding scheme. If R is very close to 1, then the coding scheme is highly efficient, but maybe it is not as protective. Whereas if R becomes close to 0, then the scheme becomes highly protective. Right? And so if I'm repeating 1 bit, let's say N number of times, then my coding rate becomes 1 over N. If I make N bigger and bigger, then I get more and more protection, but my rate goes down. My scheme becomes highly inefficient. And so as you increase N, those two non-overlapping sets can be increasingly made pretty much non-overlapping. In reality, they are never completely non-overlapping, but they can be made increasingly non-overlapping. And so you are able to overcome the effect of noise, but the price you pay is that the efficiency approaches zero. So the question is that suppose if my communication channel is flipping the bits with certain probability P, and I'm using rate 1/3 repetition code, which does this majority voting, then what is going to be the probability of bit flips that the end user will experience? And this is the math that I was talking to you about. It's using some binomial probability functions. And through that, you can derive some closed form expressions, which say that, for example, if your bits are getting flipped with 10% of the chances, and if you repeat each bit 3 times and then do majority voting, then after that, your probability of error will drop to only 3%. So from 10%, you will go down to 3%. And if you increase the value of n, then you have to use a slightly more generalized form of the formula, and it will give you what the probability of error is going to be. So let us look at what is happening. Okay, so this is the diagram that shows that suppose my channel is flipping the bits with 10% probability, and I repeat each bit 3 times. So my code rate becomes from 1, it drops to 1/3. So I get to this blue point, right? And we calculated that my error probability drops from 10% to 3%, somewhere around 3%. So my information transfer becomes more reliable, right? Only 3% of the bits that I'm sending are now in error, although the actual physical channel is flipping the bits 10% of the times. The price that I paid is that my rate became also 1/3. I'm using the channel only 1/3 of the time. The remaining 2/3, I'm just repeating the same bit over and over again. Well, what if I repeat the bits 5 times or 7 times or 9 times? I start getting better and better reliability, right? That URLLC feature, ultra reliable communication, that goal becomes increasingly better realized, but my code rate starts dropping. This is the same chart plot in the logarithmic manner. And you'll see that on y-axis, the probability of errors take a nosedive, right? They really fall off sharply. But then the price that I pay is that my code rate also drops and it starts becoming close to zero, right? On one hand, on y-axis, I get performance benefit, a tremendous benefit. My probability of error, I can make it to be as low as 10 to the power minus 15. Out of 10 to the power 15 bits that I transmit, on average, only 1 bit will be in error. The problem is that my code rate, according to this graph, has to become extremely small. This is the same chart plotted in that region. And you will see that to get ultra reliable communication link, 10 to the power minus 15 type of error rate, my code rate has to be 0.016 or something, right? So the rate becomes very low. Take an example that suppose actually my data is suffering from 10% errors. And I would like to design this repetition code that reduces the effective error rate to 10 to the power minus 15. I will need to repeat each bit 63 times, 1 over R, 1 over 0.016, which is roughly 63. So that is the price I pay. To give an example, suppose I have a movie stored on a DVD, and let us say that the DVD technology, maybe the DVD driver, is such that it messes up 10% of the bits. And still I want to watch the movie pretty much as if there was no noise. Then that one DVD, I will have to have effectively 63 DVDs. A movie which can be stored in one DVD will require 63 DVDs because each bit I am repeating 63 times. So my data size becomes 63 times more. I will still get pretty much zero error rate, but then this is the price that I pay. Okay. Now, over the next 10 minutes or so that I have, I want to emphasize the technological innovation that was brought about pretty much single-handedly, okay, by an engineer named Claude Shannon. So Claude Shannon was an engineer working at Bell Systems, Bell Labs in New Jersey back in 1940s, maybe 70, 80 years back. And he looked at this problem in a deeply conceptual manner. He developed not only the concepts, but the mathematics behind it. And he, as I said, pretty much single-handedly revolutionized the whole technological domain. And his underlying ideas are still today, when we talk about 5G or 5GB or 6G, the ideas that Claude Shannon developed are even today driving the technological growth. A lot of scientists and engineers in the communication domain, signal processing domain, wireless system design, they consider Claude Shannon as effectively equivalent of Albert Einstein. Okay, he's called father of information theory, and what he proposed was, in those days, it was considered mind-blowing, sort of like how Einstein revolutionized the concepts of space and time. That is how Shannon revolutionized the concept of information transfer over a noisy communication channel. What he said is that, the general belief that if I want to reduce the error probability to near zero requires that the rate becomes close to zero, but basically the efficiency has to drop to pretty much zero efficiency. My use of communication link has to be made highly inefficient. Only when I do that, my error rate can approach zero. That is what we were just describing through the slides. What he said is that no, right? He said, actually, you can achieve zero error rate. Okay, a communication link that is ultra reliable without without making R to become zero. And so if I consider this chart, which is where the technology was, which is where everybody's understanding was before Shannon entered the picture, Shannon came along and said that I can give you ultra reliable efficiency if my rate is around 0.53. So instead of making the efficiency, the rate, pretty much drop to zero, we were talking about rate of 0.016. Shannon said that I can make rate as much as 0.53, much better than 0.016. Instead of repeating each bit 63 times, maybe I will need to repeat each bit just 2 times. And still I will be able to achieve arbitrarily close to zero type of error probability. And he came up with this function, which is known as the entropy function. And through that, he showed that instead of the blue chart, we can operate close to this red chart. And that is where the whole name of the game has been since Shannon developed this theory. how to move from this blue chart, which we can do easily, right? To get any point along the blue chart is not difficult. You just repeat the bit n number of times. And at the receiver, you just do majority voting. To go from blue to red has been the technological challenge of our times, of our past 60 or 70 years. And a lot of the advances have actually happened in last 10 or 15 or 20 years, in fact. And today, maybe for 3G, I'm just making it up a little bit, but not entirely inaccurately. I would say for 2G and 3G, we were somewhere over here. And for 4G, we came somewhere over here. And for 5G, we are this close to the red line. Okay. So how are we doing in terms of time? We have maybe 4 more minutes. I think we should, maybe I'll stop here at this time and I'll take up questions if you have any. And then I'll continue from this point on when we do the second part of this talk. Okay, so somebody asked why n is only 1, 3, 5 odd numbers only. What is the logic behind that? It's a very good question. See, n equal to 1 is pretty much non-repetition. You are not repeating the bits at all. So there it is not an issue. Why don't we do 2 bits repetition or 4 bits or 6 bits? We can do it, but there is a slight advantage if we do make use of only the odd numbers. And the reason is because, as I said, the receiver operates by doing majority voting. So suppose you repeat each bit 2 times, or let's say 4 times. And then at the receiver, you get 2 zeros and 2 ones. Or if you repeated each bit 6 times and you get 3 zeros and 3 ones, you don't know whether to believe that bit 1 was transmitted or bit 0 was transmitted, because both are equally probable. If you have equal number of zeros and ones, the majority voting decoder will get confused. But when you repeat each bit odd number of times, it can never happen that the number of zeros and number of ones that the receiver gets are equal. And so there is a slight performance benefit of repeating a bit odd number of times. Okay, let's see. I hope that that answers the question. Are these researches on 5G happening in India or international level, combining all the countries? So everywhere, right, all over the world, there are a very large number of research groups, both in the academia as well as the industry, that are very, very active on 5G and beyond technologies. In India, all the IITs, IISc, many universities such as DISCT and NIRMA here in Gujarat and other universities, there are a lot of researchers active in this domain. There are many technical conferences that are focused on 5G advances. There is actually one conference happening at IIT Gandhinagar in about a month or so, IEEE ANTS. There are conferences such as SPCOM and national communication conferences that happen at different IITs and IISc. So yes, there are researches going on in India, but at international level, there is again a great number of initiatives, conferences, journals, research groups, even industrial advances that are happening. Okay, so the answer is yes, they are happening both in India as well as abroad. What is the current coding scheme used in 5G? And so there the answer is it is LDPC, and tomorrow, maybe in the first 5 or 10 minutes, I will describe how this repetition code becomes kind of a module of this LDPC codes that are used in 5G. Okay, so the low density parity checking coding scheme, which has been introduced starting 5G until 4G, the coding schemes were different. In 2G and 3G, the standards used what is known as convolutional coding. Then maybe around 3G to 4G versions of these standards, people started using what are known as turbo codes. And then 5G and beyond are relying on LDPC codes and polar codes. Okay. Who drives the standard of communication, right? So that is a good question. Again, as I said, there are industrial as well as academical representatives that work in a forum. They meet sometimes twice a year, sometimes once a year, or 1.5 year basis. Representatives come from all the different companies like Globecom and Qualcomm, the Huawei technology in China, Ericsson, Nokia, and there are a large number of other companies which are not as well known, as well as companies and universities that are active in the area of communication design. If we are near the orange line today, does it mean that there will be no scope of further improvement? Okay, that is a very good question. Okay, so when I say that we are close to the orange line, what I meant was that we, in certain instances, we come close to the orange line. So I just mentioned that a 5G uses LDPC codes and polar codes, right? LDPC codes are considered very good if the block length is very large, right? That efficiency ratio I was describing, R equal to K divided by N. So if K is large and therefore N is large, then the LDPC codes are good. But when K becomes small, so suppose you have a sensor and that sensor collects only a tiny bit of information at a time, maybe 2 bytes or 4 bytes, maybe 16 bits or 64 bits or even 128 bits at a time. If you want to transmit small number of bits, then the LDPC codes don't come very close to the orange line. Okay. And so that is where the new advance that happened in 2007, polar codes, came into becoming part of 5G. Because polar codes are better in approaching the orange line, even when the data size is small. Right? If you're transmitting large data packets at a time, maybe you're doing some video transfer or image transfer, and you can send at a time maybe 20,000 bits or 64,000 bits, then LDPC codes are fine. But then if you're looking at smaller block lengths, if you're trying to improve upon the computational complexity of the decoding algorithms, then maybe there are some other alternative technologies that are possible. So no, the answer is that there is still a lot of scope in terms of further improvement in terms of the coding technologies. Before continuation to Claude Shannon's channel encoding in the next lecture, what should I revise from engineering mathematics that will help me understand fully? I would say that I didn't keep these lectures to be highly mathematical in nature, but I think it will be good for you to, for example, understand the derivation of the error probabilities that I did. How did we go from 10% to 3% by repeating each bit 3 times? Right? That will allow you to appreciate the challenges that are involved in achieving ultra reliable communication in presence of the noisy channels. Right? So that a brief understanding of some probability math will hopefully better allow you to better appreciate the challenges that are involved in realizing ultra reliable communication and why it is so difficult to do it. When battery operated smart devices, mobile devices come into picture, what is the optimization required to support 5G, as it may drain battery faster than LTE? Component level, where do we need more changes, at hardware or at application level? Okay, so there again, I think similar to the earlier question, which was that if you are near the orange line, will it mean that there is no scope of improvement? I answered it by saying that we are close to the orange line from when we approach the problem from one angle. But the actual problem is multifaceted and it has many, many different angles, right? And so some of the angles are optimized, some of the angles require still a lot of optimization. The same way in terms of battery optimization, there are many, many different angles from where you can approach. The problem itself is multifaceted. And so there is no one answer. There is obviously a component level optimization where you improve the battery technology. There is an application level optimization where, for example, the application itself makes minimal use of or only as needed basis use of technology. But then there is underlying communication technology level enhancement, which is the type of enhancement that I was alluding to earlier, where, for example, one simple technique would be to just reduce the duty cycle. So you don't transmit, you don't keep the transmitter on all the time. You switch it off either in a as needed basis. So when there is nothing to transmit, you switch it off, or you switch it off in a deterministic manner, in a periodic basis. And so if you use, for example, duty cycle of 1/3, well, maybe that is kind of a little bit reverse of repetition by 3 coding, right? 2/3 of the time you switch off the transmitter, you transmit only 1/3 of the time. And then there are other advances like what I mentioned, the energy harvesting or wireless delivery of the charging. So those are some of the communication-centric advances that are happening in terms of improving the battery efficiency. The next question is, in a 3-bit repetition to detect through majority vote, one last combination was not able to detect originally transfer. Yeah. Okay. I think you have noticed it well. In fact, I made a typing mistake in that repetition coding example that I had given you. And thanks for noticing it. See, the majority vote decoder diagram that I had shown, the one particular combination that you are referring to, it should belong to the second subset, not the first subset. Okay, so once you do that, the issue that you are pointing to will get resolved, right? So it's a good catch. The next question is, what is the main challenge in achieving getting close to Shannon equation for low error rate, right? Again, a very good question. So what Shannon did, the revolution, the technological paradigm shift that he ushered in, is a type of mathematical advances that are called as non-constructive proposals, right? So what he proposed and what he actually, in fact, proved mathematically, that proof is a non-constructive proof. Using his proof, nobody can design a technology which will allow them to get close to the limit that he had pointed out. I don't think the analogy would work very well, but it's sort of like basically Shannon established a limit, that orange line, and he said that nobody can cross the orange line. But how to approach the orange line is completely unstated in Shannon's paper, although he gave some hints. And one hint that he gave through his mathematical proof was to say that don't transmit a bit alone by itself. If you transmit a bit by itself, it is going to be next to impossible to protect it, right? That is why if your BSC is introducing 10% errors, and if you transmit 1 bit at a time, then you have to live with 10% errors. What Shannon showed is that instead of transmitting 1 bit, if you instead transmit a sequence of bits together, and make it a code, right? A very, very simple code is this repetition code. It transmits either 3 zeros or 3 ones, nothing else. Or if it is repeat by 11 coding, you transmit 11 zeros or 11 ones, nothing else. What Shannon said is that if you transmit bits more intelligently than just repeating them, then you can get pretty close to the orange line that that was shown. And the challenge there is that you can come up with some coding scheme, right? The coding scheme, the name is essentially that when you are transmitting some bits, you don't transmit them just like that. You encode them. You convert them into some other sequence. And that process of converting them to other sequence, that is known as coding, right? I mean, all of us, or rather most of us, would have played some such game in our childhoods where for example, I am talking to my friend, but I don't want my friend to, I don't want anybody else to understand what I'm talking to him. So I would devise a code, and I will, instead of saying something straight away, I will convert it into code. Nobody else will be able to understand what I'm saying except my friend. So that is an example of coding. And that is what is used in today's encryption technologies. So similarly, Shannon said that you have to do some coding. The challenge is that, yeah, fine, I can come up with some code, but I don't know how to decode it in a computationally efficient manner. If I want to approach this orange line, then I will have to come up with a code which is so complex that decoding it in today's technological capability might become extremely difficult. So that was the main challenge. The reason why, until the advent of LDPC codes or the polar codes or the turbo codes, all the mathematicians and the engineers who were working on solving the problem stated by Shannon, they were not able to really fully solve it, was this. They knew how to solve it. Actually, the convolution codes that were used in 2G and 3G, they are highly capable actually, and they can actually approach the orange line. The problem is that in order for a convolution code to approach orange line, at the receiver, you will need a supercomputer. You can't use your handheld device to decode such a convolution code. And the magic of today's technology, the LDPC and the polar and even turbo, is that your handheld device today is able to decode this code. Okay, so the computational feasibility was the main concern. When Nirav has asked, what is today's biggest technological challenge to solve the move towards 6G? Okay, so I would say that the interplay of the algorithms and their implementation on the hardware is the biggest technological challenge. And this is an extension of the answer that I gave just now. Many of today's algorithms are highly capable, and they are very powerful, very efficient. Channel coding is just one aspect of 5G and 6G technologies. There are multiple other aspects, some of which I will talk about tomorrow. And development of ideas in terms of how to achieve all of this technological growth goals. The ideas are there, but then the marriage of the idea with the actual hardware is sometimes lacking. Some of these ideas, as I said, might require a supercomputer to exaggerate a little bit, or at least they will require inefficient usage of the energy and the power, so that you can simply not have a practical solution. Some of them require, for example, extremely large antenna sizes, which are again not visible. So I would say that is one of the biggest technological challenge. And there, for example, there is a technology called massive MIMO that is being increasingly adopted in 5G and 5GB type of networks. In 4G, you may have heard of MIMO already, where they use maybe at the most 8x8 MIMO, 8 antennas at the transmitter, 8 at the receiver. Typically, it is even less than that, maybe just 4x2 or 2x1 and like that. The problem is that your phone, how can you make it have more than one antenna, right? Even one antenna today is not visible. People don't like to have an antenna sticking out of their phone. And so today's smartphones, the antenna is kind of invisible. If you want to increase the number of antennas, especially at a handheld device, that's a big constraint. You can't make such a requirement easily. And so that is a practical challenge. The idea is there. In case if you can implement a massive number of antennas at the receiver, then suddenly all of this technological growth goals that I had described, it becomes far easier to realize them. But this is almost a non-starter. You can't propose a smartphone with a large number of antennas. And even at the base station in 2008, a mathematician named Marzetti, he wrote a paper and he showed that if I use, instead of 8 antennas at the base station, if I use maybe 1,000 antennas, then suddenly I can solve a lot of the technological challenges. But then even at the base station, to have 1,000 antennas is a big deal. The base station will become very complicated and also expensive. And so there, one kind of a middle way out that is being explored today in the literature, even in the industry, is called hybrid beamforming. And I have published one or two papers on that. Although you use maybe 1,000 antennas, maybe you actually use only maybe 20 or 50 RF chains, and then you intelligently switch these antennas across this limited number of RF chains. It's sort of a practical realization of this mathematical end result. Nirav has asked, what is the achievable spectral efficiency in the 5G? How many number of bits per second per hertz? Okay. In the 5G employs what is known as adaptive coding and modulation. Okay, so we have talked a little bit about coding. Modulation is something that we have not talked about. Basically, this ACM, adaptive coding and modulation, it allows you to achieve a wide range of spectral efficiencies. Okay, so if suppose you are in a highly disadvantaged scenario, maybe you're far away from the base station and you are behind a building where already weak signal gets even further weakened because of the obstructions in between your device and the base station, then it is almost impossible for you to insist that I want high spectral efficiency. And so now you have to accept lower spectral efficiency. Compared to suppose now you come in front of the building and you start driving closer to the base station, your channel becomes much favorable. And now you can actually suddenly get a much higher spectral efficiency. And so one of the advances that has happened in 5G is that through this LDPC codes and through the coding technology and a combination of modulation technology, compared to what was available in 2G or 2.5G or even 3G, the range of spectral efficiencies that are possible has increased a lot. And so as an end user, you can enjoy some really large data rates when you are close to the base station in the line of sight type of situation. But then if you go behind a building, there is a shadowing blockage going on, your link actually drops pretty drastically in terms of quality. The SEM throttles down the spectral efficiency, and so as an end user, you are still able to say it little in a non-technological manner. Your link still survives, right? It doesn't crash, but the efficiency will go down. So the answer is that the range of spectral efficiency that is achievable has become much larger in 5G, and I will elaborate on that tomorrow when we go over part 2 of my presentation. Have Geo 5G commercialization done recently? Is encoding foundation in this repetition code? Yes. Believe it or not, this repetition code, which is probably one of the easiest thing to understand, all you do is just repeat the bits, and at the receiver you do majority voting. It indirectly has become part of the 5G, and this is what we will look at when we consider LDPC codes tomorrow. Is P equal to 0.1 outage probability? Yeah, so what is an outage probability, right? Outage probability is the probability at which your communication link is in outage. Basically, your link is dead at that point of time. And so whether P is equal to 0.1 is outage probability or not depends on your application. So if you are, for example, transmitting some messages which don't need to be highly reliable, then the links can still operate at error rate of as large as 10%. Typically, though, in any communication system design, a threshold today which is being accepted kind of not as a formal requirement but as an informal guideline is that if you're trying to do audio transfer like voice calls, etc., you need at least 0.01 1% type of reliability, preferably 0.1%, 10 to the power minus 3. And if you're transferring images and videos, you would want to operate at 10 to the power minus 5 or 10 to the power minus 6. And remember that 99.99999% number that I gave for URLLC application. There, the outage probability will be even lower than that, right? So outage probability depends on the application, where the application will stop being functional. And the goal of this coding technology is to convert a channel for which this probability is much higher into an effective or virtual channel where the probability of failure drops drastically. Okay, just a few more questions. Will repetition code increase the redundancy? Yeah, that R is actually telling us that. When R is equal to 1/3, it means that 2 out of 3 bits are redundant. And therefore, the rate of communication becomes 1 out of 3. In 1 over n repetition, what is n? So n is the number of bits that you repeat, right? So in rate 1 over 11 repetition, when you want to send 0, you send 11 zeros instead of just 1 0. And when you want to send bit 1, you send 11 ones, right? So you repeat each bit n times in that repetition coding. Okay, so I think that concludes all the questions that at least I can see. So with that, yes, we can maybe conclude today's session. And I ended up taking more time. I think it's already close to 4:30, so sorry about that. And I'll do the part 2 of today's presentation tomorrow at the same time.
Thank you, Dr. Yash Vasavada, for sharing your valuable knowledge with us on 5G.
Okay, thank you.
So tomorrow we continue part 2 of this 5G evolutions webinar series at the same time 3 to 4. Thank you.